All right, we're talking about section 2.2, contextualizing linear functions. Okay, I want to get into it. I want to talk about what you highlighted already and why, as well as getting into actual contextualizing. All right, let's go to work. First things first, what does contextualize mean? We talked about this previously in the last unit. What does contextualizing mean? All right, might as well define this. Contextualizing means in a situation. Okay, or in context. You talk about context in your English classes and reading. Okay, if somebody takes what you say out of context, they change the meaning, right? So when we're talking about contextualizing linear functions, we're talking about looking for this information in a situation, okay, and what happens in a particular situation. We're trying to take our math here and apply it to the real world. Because remember, math is not just numbers, it's problem solving and logic. Problem solving and logic. All right, so first, we defined a linear function in several ways, okay? We defined it as the graph is a straight line. That's obvious. Thus the name, linear. We know that it has a constant rate of change. Our favorite form is y equals mx plus b. Who can tell me the name of that? Slope-intercept form. There we go. Where m is the slope and b is the y-intercept. Somebody give me another name for slope. Come on, quick. Rate of change. Rise over run. Both good ones. Okay. Give me another name for y-intercept. Come on. Initial value. Initial value or the constant. Okay. Now, so that's what we're looking for. We're looking for rate of change and initial value. Rate of change, initial value. Rate of change, initial value. Might as well get used to that because that's all we're looking for in this entire chapter. Okay. Linear functions are, write this down, functions to first degree. I don't like that it never says that, but linear functions are functions to the first degree, meaning there's no exponents. Okay, all the exponents are 1. All right. We've been talking about your x and your y. We go x and y, input, output, independent, dependent, domain, range. Remember, we've been doing that since the first week of school. Those things are still true. Our input is our independent variable. It is also our x value. It is also our domain. All those things. We've been talking about it all year. It's not changing. Our output is our dependent variable. It's our y variable. It is our range. Nothing has changed there, okay? This stuff's starting to creep its way into your brain, I hope, okay, because it's not changing. What we're trying to do is we're trying to decipher what the input is and what the output is in different forms of a function. For example, 1 here. The number of grapes depends on the number of branches of a main vine represented by this equation. Without looking at the equation, what's the input or the independent variable? Well, G depends on what? B. So what's the independent variable or the input? B, the branches. We can also see that is 100 times B, right? That's the input. That's where our X normally is, isn't it? That's cool. And then what's our dependent variable? G depends. Notice that's where our Y normally is, of Y equals mx plus B. Looking at this one, if we look at the equations, it should become very easy to see what's the input and what's the output. Here, what's the input? C. What's the output? G. What's the rate of change? 25 over 3. What's the initial value? 0, right? There's nothing there. That's 0. Looking at the third way, what if I'm given a graph? What if I'm given a graph? What is my independent variable? The x, or in this case, it's the m. And my dependent variable then is my c. Okay. Now, what is my initial value? 20. Right there. It's my initial value or my y-intercept. It's 20. And what is my rate of change? I go up 10 over 1. So 10 over 1. And we can see those things to be true in the equation. Now, we're going to be given a graph and have to come up with the equation. Or we might be given an equation and have to come up with a graph. Or we might be given a situation and have to come up with an equation or a graph. Or we might be given an equation and have to come up with a situation. That's what this is all talking about. Everything that we're dealing with, this contextualizing, is looking for what's the input, what's the output, what's the rate of change, and what's the initial value. We are looking for y equals mx plus b. If we can find all 4 of them, we're golden. We have everything we need. But what if we can only find 2? Or what if we can only find 3? Well, if that happens, Dylan, then we are good because we can fill in the equation and we can choose our own inputs and our outputs depend on the situation. Okay. So let's do number 1 together. Okay. Let's look at what we need to identify. We need to identify the rate of change, initial value, independent variable, and the dependent variable. I want to also call that input and output. Okay. Then describe what the rate of change and initial value mean in context of the situation. Finally, write the equation. Well, it's no problem to write the equation once I know what my input and output are because I'll use y equals mx plus b. I'll use that form every time. All right, let's look at our first situation. Okay, I'm going to hide something here just for now. I don't want you to see that just yet. Okay, so let's look at the situation. A 2.5-foot rocket, distance traveled in meters based on the time, is modeled by the following function. Okay. What are my variables that I'm going to use? D and T. Which one's independent and which one's dependent? Which one's the input? Which one's the output? D is the dependent because it's based on the time. So D is my dependent variable. That makes T my independent variable. So what are the 2 things I'm looking at here? I'm looking at distance and time, right? Looking at distance and time. Distance and time. All right. What else do we know? What else do we know in this equation or in this thing here? What's 2.5 feet? The rocket. What do you think that is? Is that a kitten or is that initial value? That's my initial value. That's how tall it is. So my initial value is 2.5. Only thing I don't know is my rate of change. So right now I would know D equals something times T plus 2.5, right? Because the only thing I don't know is my rate of change. But look what I covered up. I covered up the equation. What was the equation? So my rate of change is 5. Gee, I wonder why they made initial value 2.2 instead of 2.5. I don't know. Maybe they buried it down a half foot into the ground. I don't know. All right, so what's the rate of change? 5 meters per second. How do I know meters per second? Meters and in seconds. Okay, that's how fast it's traveling. And what's the initial value? 2 feet. Maybe, even though the rocket's 2.5 feet tall, maybe they build a platform and put it 2 feet above the ground. That could be, right? So 2 foot, I'll call it a platform. Now, if this was a test, I would want to tell you why I thought it was that. You know what I'm saying? Just to make sure, because I think we could sit here and argue whether it was 2 or 2.5. Cool? Think you can handle this? Yeah, we're about to find out. Evens through 18. So you have a whole 9 problems to do for homework. Okay? 2 through 18 even, and then what? Watch the video. I think it's going to be very, very important for you to watch this video. Is that clear? And if you want to do one problem and watch the one video, and one problem and watch the one video until you feel like you're getting good at it, I'm okay with that. That's a good plan. Got it? All right, you've got, looks like about 15 minutes. Get started. If you got questions, I'm here for you. Have a great day.